So this section is 3.3, measures of position. So we're talking about how numbers or data values compare to other data values in terms of where they lie in the set of data. Okay, and we're going to look at that in lots of different ways. The first way that we're going to look at that is something called the z-score, sometimes known as a standard score, but to be honest, we don't ever use that phrase. It's always just a z-score. And it's obtained by subtracting the mean from whatever the value is we're talking about and dividing by the standard deviation. And this connects to what we did with Chebyshev's theorem in 3.2. Because when we were trying to find the value of k, we did this. This is exactly what we did. And formula, the general formula, that's what it is. Z equals whatever the value is, that z-score, minus the mean, divided by the standard deviation. This was the way we found k in 3.2. Now I'm going to put a couple other formulas up there, just so you have the notation and you see it. And if you're looking through the book working on this, that you know what that means. But the truth is, this formula that's there right now is the one you really need to know. Because these ones are all just different situations. You can write as much of this down as you want to. It's really not that important. The distinction that's being made is that if we have a sample, okay, the notation is different, right? We take the value, whatever the value is, subtract by the mean. So x with the bar is mean for sample, and s is standard deviation for sample. If we're in a situation where we're talking about a population, bless you. If we're talking about a population, now we're subtracting the mean, which the mean now is lowercase mu. So it's the value minus mu divided by lowercase sigma, which is the population standard deviation. The key to this, as I said, is this is what you need to know how to do. These are just different notations signifying a sample situation, signifying a population. And the other thing that's important is the z-score is the number of standard deviations above or below the mean. So like we talked about in Chebyshev's theorem, the k value was the number of standard deviations that we were looking at. And that's what the z-score is. It's the number of standard deviations above or below the mean, which means I can have a positive value if it's above the mean. I can have a negative value if it's below the mean. Oftentimes we use z-scores when we're comparing apples to oranges, so to speak. We did that a little bit when we talked about coefficient of variation, when we have two different kind of groups. You can still standardize, that's why it's also sometimes called a standard score. Standardize a score or a data value in relationship to where it's positioned to all the other data values. And that's what the z-score is all about. Other questions about that? All right, let's look at an example. If you want to take a picture of this, feel free. We're going to compare test A and test B. This might be a situation in this particular problem where we're talking about test A being, a statistics class and test B being a Spanish class, right? We don't know how many points each test was worth. The only thing we know is what a particular individual got. So on test A, they got a 38 out of something, I don't know. And we don't even know if it's a percent or a raw score, we don't know. And for test B, somebody got a 94. Now, what they tell us about each of the tests is they tell us the means and the standard deviations. And so the mean for test A was 40, which means it obviously was worth more than 40 points if this is the average. And same with B. If this is the average, then the test was worth more than 100 points or 100%. I don't know. Extra credit, whatever. Okay. then the standard deviation here is 5, and the standard deviation here is 10. So what we're going to try to do with this problem, and in most of the problems, is we're going to figure out, one, we're going to find the z-score, and then we're going to state which z-score is higher, relatively speaking to the rest of the class. Okay? So for test A, what we're going to do is we're going to take the value, my particular value, and this one we're looking at is 38, the mean, subtract the mean, and I'm going to divide by the standard deviation. So what do I know, before I do all the calculation, what do I know about the value of the z-score for test A? What kind of number are you going to get? Say it again?
Negative.
Negative. You're going to get a negative. Okay. Are you going to get a negative for test B? Yeah. So both of these scores, obviously both of them are below the mean. What we're trying to see is which one is further away from the mean. And the one that's further away from the mean is going to be lower. The one that's closer to the mean is going to be higher. Okay, so let's do the first one. So the first one is 38 minus 40, because it's the value minus the mean divided by 5. So go ahead and do that one. All right, so here's what the work will look like for this one. Okay, so you've got the value minus the mean over the standard deviation, negative 0.4. How many got that? Okay, good. Do we think test B is going to be higher or lower than that? What would you guess? Lower? Why do you say that? You have no explanation. You're just guessing. Okay. Anybody have an actual explanation why they think it would be lower? Yes.
Because it's a bigger negative number.
But the standard deviation is also bigger. So let's look at that. Let's think about it. Let's kind of predict. Okay, the difference between these two is 2. The difference between these two is 6. So this one is 3 times as big, right? If the standard deviations were 3 times as big, what would be true about the z-scores? They'd be the same, exactly. Now, since the z-score is only 2 times as big, we would expect this one to be lower. So you can predict it. I mean, you don't have to. Sometimes I like to look at problems and try to figure out the answer before I actually do the work, just to kind of see if it makes sense, if it's reasonable. And so in this case, when we do test B, okay, 94 minus 100 over 10, that's negative 0.6. So which one of these is higher, test A or test B? Test A, right? Negatives work opposite. So this one is further away from the mean. This one is closer to the mean. So the number of standard deviations below the mean, it's closer to the mean. So in this case, test A is higher, relatively higher. And when we say relatively, we're saying in comparison to test B. And that's what you do with z-scores. Now, obviously, if somebody had a positive z-score, that one will always be higher than a negative z-score. Okay, so that's one of the things you're going to have to do in your homework for tonight. One of the main things that we will talk about in 3.3 is percentile. And I want you to think back to the first time you ever heard the word percentile. When was it? Where were you? You were probably a little kid. Let me see. Actually, wait a minute.
Specifically, I was 2 years. No, I don't know.
Okay.
I don't remember.
Yeah, I was saying, you don't remember the first time you heard the word percentile?
No. I think 4th grade, 5th grade.
Standardized test, yeah. Where you compare, that was definitely one of them. I bet you heard it before then, though.
I think it's middle school.
No, even way before that. Like, you were a little kid.
I don't know. I had to be
It wasn't in school. It wasn't in school.
Was it in school? Oh, in the doctor's office?
What do you mean?
Like, your health. I don't know.
Like, what about your
Like growth? Your height?
your height, right?
And your
We
weight.
talked about that all the time. How many of you remember feeling like they said, Ethan, were you really tall when you were little? Have you always been tall? Because you're tall now. Yeah, so were you like in the high percentile for height? Do you remember that? Do you remember what it was? No.
I'm in the 80th.
You were in the 80th when you were, when
Still am.
you are still.
I think so.
Awesome. All right, Dakota, for example, you're not very tall. Do you remember what percentile you were?
I don't know. They just said that you're not going to grow very much.
Okay.
I remember being like 5 percentile for weight when I was like young.
Oh, okay.
Yeah,
All right.
yeah.
So good. Now, we can talk about where your percentile is, but let's talk about what that means. Okay. So percentile is in relationship to all the other in that grouping. So all the 10-year-old kids, for example, if you were the 20th percentile, that means you were taller than 20% of 10-year-olds. Okay? So first off, it's positional data because it's all ranked together. And it's broken up into 100 equal groups. That's what a percentile actually is. So we take all the existing data for a set, and we divide it up into 100 equal groups. And then an example, like we were talking about, if you're the 80th percentile for height at your age, then you're taller than 80% of all the people. So Eva said she was in the 80th percentile. So for girls her age, she's taller than 80% of girls her age. Okay, where in the world, in the state, in the country, we don't know. Just it's a generalization. Okay, and they've taken data over many years to determine that. Now, in a case like that, they use that to make predictions. Sometimes doctors use that because they're concerned, like if you're really low for weight, for example, there's sort of a quote unquote normal range that you're supposed to be in, and so if you're really light for your age, doctors might become worried, or the same, they might be worried if you're really heavy for your age in that particular thing. But I'm not a doctor, so I don't know. But that's how we think about percentile. And then we know some notation. What we do is it's P1 for the first percentile, P2 for the second percentile, and so on. Third, 99th percentile. Yeah, definitely in the testing, I can remember, now granted, the testing that I had to take when I was a kid versus when you were a wee lad are very different, right? But oftentimes they would look at how you do on those scores and or on those tests and decide maybe where you should be placed, what kind of level you should be placed into. I know they do that for reading, I think still now, and they decide what kind of reading level you should be at based on your percentile on a particular test. And the higher your percentile was, the higher the level you'd be placed in. So I still think they use that. I'm not sure anymore because I don't have elementary age children, but I'm guessing that probably hasn't changed too much. There are 3 different ways that we're going to use percentiles and calculate percentiles. One of the ways we're going to use today in the next couple days is using a graph, okay? And so if you remember, I think I still have it here. Let's see. Don't worry, you're going to wake up fast here in a second. What was on the notes, the last page was not that important. It's okay.
Yeah, well, I like writing all of it.
Well, I can go to the video if you want.
You know what? That's what I'm doing. Don't be mean. I'm in the battle right now. I hate You're a dog. You're like,
And then you.
you're like, oh.
All right. So that first one is just 24. Then we're going to add them as we go. So what's the next one going to be? 86. Very good. What's the next one going to be?
158.
One what? 58. Then what after that?
184.
184. Then what? 196. And then what does the last one have to be? 200. So when we add them up, it should equal the grand total. All right. Now, in a cumulative frequency distribution, oftentimes we stop here. When we would do a relative frequency distribution, we would often convert it to a decimal. In this case, for a percentile graph, we're going to convert it into a percent. So everything that we're doing here is really the same from chapter 2. So when I figure out the percent for this first one, what am I going to do? Oh, here it is nicer, by the way. What do I do for the first? How do I find the cumulative percent for this very first one? What would I do?
Divide 24 by 200.
24 divided by 200, which is going to give me what as a percent? 12%, which just so happens to be, since this is out of 200, if it was out of 100, then this would be the percent. But since it's out of 200, I just have to divide it by 2. Okay, so what's the percent going to be for this one? 43. What's the percent going to be for this one? 79. 92, 98, 100%. Okay, so these are percents now. And there's a reason that I underlined the end boundary, the upper boundary, and the percent. And that reason is because those are the points I'm going to graph on my ogive, on my percentile graph. So for example, on this first line, I'm going to be graphing the point 104.512. Now, if you remember when we graphed ogives, we had to start at the x-axis. So the very first point that I'm going to have is going to start here. So I'm going to have 89.50. That's the only time we use the lower limit. The rest of the points come from the upper limit of the boundaries, and they pair up with that percentage. This is what you would have to do in your homework. Now, I'm going to provide you with the graph for this just in the interest of time, but this is going to take you a little time to do when you get to a problem like this in your homework. But I want to show you how to use the graph to find certain values. So that's going to be on the next page. So I want you to, I'm going to put that up here. I'm going to take a picture of this. That's the percentile graph. Notice the 89.5 at 0 down there. Okay, go ahead and take a picture of that. Get that in your notes. Then we'll talk about how to use it. We can find a percentile for a specific value. So for example, if I was looking for 160. Okay, if I wanted to figure out what percentile 160 was, I could just kind of go up to the graph and be like, okay, 160, that's like the 90th-ish percentile, okay? I can go the other way. What value is the 60th percentile? So the 60th percentile is here. I would go over, and then I would say, oh, it's about 123 or whatever, okay? What's important here when you do this for your homework is that unless you have the exact same percentile graph as the person sitting next to you, you could actually come up with a slightly different answer for the particular problem than the person next to you, okay? So be careful on that. There are more than one right answer. When I show you the correct answers, just know it's possible that you could have a different answer than someone next to you and that they're both right. Because how your graph looks may change from person to person. Ready? Okay, so let's find the 40th percentile. Let's figure out what value is the 40th percentile. So in this case, what we're going to do is we're going to start over here at 40. And we're just going to draw a horizontal line until we hit the graph. Okay, it's going to look something like that.
I erased all of those lines. Just like
Okay? And so then what I'm going to do is I'm going to then draw a vertical line from that point and try to figure out where it hits the x-axis. And this is where I'm talking about we're making an approximation. I've approximated that that's 118 millimeters of mercury. Now, you might have said 119, and that's fine, okay? It doesn't have to be like that, but it can be like that. The other thing that we can do is go the other way. So like I said, let's see what percentile. So this, the 40th percentile is that. I want to make that red. Sorry. Okay, so that's the 48th percentile. If I wanted to know what 160 millimeters of hydrogen was, what I would do is I would just draw a line from where I think 160 is. Whoops. .160 is right in about there. And does that seem like a vertical line to you? Looks good to me. And then I'm going to go over from there. That's a little tilty, isn't it? That's close enough. You get the point. And this is important because this is where we could have those variations, right? I'm going to say that this is the 92nd percentile. So you can go the other way too. If you wanted to say 91, you think it's closer to 91, that's fine. Okay, it's not that big of a deal. But you can go in either direction. Okay, so I can go from the value to figure out the percentile. I can go from the percentile to figure out the value. And there's going to be a problem. I think it's number 19 today. It'll say find the percentiles of the certain something something, and you use the graph that you made in 18 to find that. That's really what's going on. So that's the first way to use percentile. Okay, are there any questions about that? Again, it's just making an ogive. We did that in chapter 2. All right, the next way that we're going to find percentile is we're going to have a list of the data. And we have a formula. And the formula is as follows. We're finding the percentile of some value x. One of the values in there. We want to know what percentile it is. The formula is we count the number of values that are below x, add a half, divide it by the total number, then convert it into a percent. Okay, so that's the formula. So here's some data for you. We're going to use this data over and over again through the course of this example and the examples that follow. So here's some teacher. They gave a 20-point test to 10 students, and there are their scores. We're trying to find the percentile rank of somebody who got a 12. Now let's take a second just to look at this test and these scores. Is there anything about these scores in this particular test that maybe is interesting to you?
Well, that's.
Some of these kids are stupid.
Some of these kids are.
These kids are stupid.
They
Yes.
need a 2 out of 20.
Yeah. Okay. So, is there anybody in here? I know this is going to be a reach, and maybe you don't want to admit it yet. Is there anybody in here who thinks they want to be a teacher? I know. When I was sitting in your seat many years ago, I would have reacted the same way, and look at me now. Anyway, yeah, this is not a good situation, right? Either
It's going to cut your salary.
this teacher does not know what they're doing because they don't know how to write a test, or nobody cares. We can't have a test where there's 118 and 120 and all the basically rest are failing. That's not good. That's a bad situation. I guess 12 is not failing, but anyway. There's a 15. All right. There's 4 that are not failing grades. 12 is basically a failing grade, but it's not technically. All right. So what do you think I have to do with this data first? Huh? That all just sounded like noise to me because you all said it literally exactly the same time and you didn't say the same thing. Yeah, organize it. How? Least to greatest. Put it in order from least to greatest, please. Do that now. So we're talking about the number 12, and we want to know what percentile that 12 is. So this is one we're focused on, first of all. And then I have to count the number of the values that are below it. So how many values are below 12? 6. There's 1, 2, 3, 4, 5, 6. 6 values below. Okay? And that's what goes up in the top part of the formula. I have to add a half to it. I have to divide it by the number of numbers. And then I have to convert it to a percent. Okay? So, this is where I'm starting. There's 6 values. Add a half to it. Divide it by 10. So this is 6.5 divided by 10, which is 0.65. Convert that to a percent, and you get 65%. Which means I skipped the multiply by 100. I did that one in my head. 0.65, convert to a percent. That means that 12 is the 65th percentile. So that's how you find percentile of a specific value in a data set. You use that formula. Now, if we go the other way, and we're trying to find which data value is a particular percentile, we have a different formula that we have to use. Okay? And just to finish off on this one, this person, they're 12 out of 20, they're 60% on the test. The barely passing D was still better than 65% of the class. That was either a horribly written test, or it was a pop test, or the teacher does not know what they're doing. If only, it's just, yeah, I'm sorry if that was triggering for you. But yeah, anyway. So this is why, like, for example, when you guys get upset with me that I hide all the averages and the highs and lows, you're looking for this. Because if you got an 8, you're feeling pretty good about yourself on this particular test. You're like, this teacher did a really kind of poor job creating an assessment. So 8's not that bad. Or even a 12, I got a 60%, but I'm still better than the 65% of the kids in my class. So yeah, that's why you look at that, because you want to make sure that, you did satisfactorily. All right, let's go the other way now. I'm going to go back here. So if this was the data set and you needed to find all the different values, there are no values below, so you put 0 plus 0.5 divided by 10. This one, there's 1 below, 2 below, and you just kind of keep going and use the formula over and over again. There's going to be a problem like that in your homework. The other way is, it's the same data set. Okay, this is the same data set, not a new data set. Still in order. And now we're going to find the 25th percentile. Okay, and the way that we do that is we're going to come up with, this formula tells us how many values or which value you have to count to get that particular percent. That's why it's C. So we're going to compute this. And the formula is the number of values you count equals N, which is the number of values, times the percentile that we're looking for, in this case, 25, divided by 100, because then we convert it to a decimal, right? So we're going the other way now. In the other problem, we had to multiply by 100 to turn it into a percent. Now we're going to divide by 100 to turn it into a decimal. Okay? So we're really just multiplying the number of numbers times the percentile. If you just convert this to a decimal right away, you don't have to mess with the 100. But, it's up to you. Whichever one works for you, I don't care. Again, what we're going to do is we're going to take 10, because there's 10 values. We're going to multiply it by 25 and divide by 100. Or you can take 10 times 0.25. Either one gives me the same thing. Okay, which is 2.5. Well, here's what you do with that 2.5. You round it. And in this case, what do we round to? 3. So that means the third value is the 25th percentile. So you round up. The third value is the 25th percentile. Well, which one is the third value? 5. So 5 is the 25th percentile. I'll write that. So that's why I say the C stands for counting. You count up to whichever value it is. Now, in your homework today, you're going to have a problem where you're going to calculate the percentile of every number in a data set. There's going to be one that has like 6 values. And so you'd say, for this first one, there's no values. Total number of values is 10. The percent, that would be the other way for that problem. So we would do that for I'm going to go back for a second so that you guys are clear what you do on that. Because I meant to talk about that. One situation with problems like this that you have to look out for. So that's why I say this is the kind of third way to look at it. That situation is when the number does not turn out to be a decimal. Sometimes this value will turn out to be a whole number. And when that happens, you have to do something different. So long as this is a decimal, you're good to do this. And just pick off the third value or whatever the value is that you round to, and you're good. When it's an actual whole number, like the next problem is going to be, you have to do something different. So there's one exception, and that's going to be, in this case, here's an example, the 60th percentile. Again, same data set, not a new data set. 60th percentile, so you take n, which is 10, times p, which is 60 over 100, or 0.6. Okay? And so I get 6. Now, what your instinct is going to be is you're going to pick the 6th value, and that would be wrong. Okay? This is the exception. When it comes out to be a whole number, the percentile is between that number and the next one up. Meaning, it's between the 6th and 7th, in this case. Okay? Between the 6th and 7th value. So the 6th value is 10. 1, 2, 3, 4, 5, 6. 7th value is 12. So it's in between. So when it comes out using that formula to be a whole number, it's usually not going to be one of the data values. The only way it could be is if the 7th value was the same. So for example, if this was also 10, then obviously in between the 6th and 7th is still 10. But usually it's going to be an average. And in this case, the average of these two is pretty easy to do, right? What's in between 10 and 12? 11, okay? So in this case, the 60th percentile is 11. That's the one special case when using that formula. And that will show up on your test, just FYI. I'm going to tell you that. So just be careful on that case. I will fix that for you. It was a typo, I'm sorry.
Just for next year.
I appreciate you. A whole number. And now the spacing's off, so that probably messes with you even more. Which messes with you worse? An whole number or A with the inappropriate spacing? Right?
Probably
Is it kind of 6 of one, half dozen of the other? That you've never heard that phrase before? 6 of one, half dozen of the other? Because right, half dozen is still 6. It's the same thing. Is this worse or the other one worse? And if the answer is they're kind of the same, that's why I use
No,
that
because I can
phrase.
deal with that because I can read that normally.
Yeah.
Okay. Well,
It's still jarring, but it's not as bad as Anne.
Okay. Good to know. I'll fix that for next year. All right. The next part's going to go fast because there's other kinds of, because we've talked about quartiles. I had to teach you quartiles the other day, and so we're going to talk about quartiles a little bit, so I'm going to go through that fast. But there's one other thing we haven't talked about yet there, deciles. Okay, so percentiles are per 100. Quartiles were per quarter, or per 1/4. What do you think deciles are? Per what? Per 10, yes. So every 10th percentile is 1 decile. In other words, the first decile is the 10th percentile. So we put D sub 1 equals P sub 10. What's the next one going to be? D2 is going to be the same as what? P20. What's D3 going to be?
P30.
P30, etc. You get the point. There's one here that's kind of special, though. Let's talk about it. D5 is what? In percentile? 50th percentile, right? What is the 50th percentile? When half is below and half is above, what do we call that? What? Say it louder. Median, correct. That is the median. And actually, this is also the second quartile.
Wow.
All those are the same. I know we only talked about the first quartile and the third quartile, but there actually is a second quartile, and that's the median. All right, so those are deciles. Now, on the next page, I have quartiles. And we've already kind of talked about quartiles and interquartile range. So I'm not going to talk about that. I'm just going to put it up here. If you write this down, you can. Okay, but just as a comparison, or if you want to take a picture, that's fine too. The first quartile is the 25th percentile. We just did this on the last page. And remember, the first quartile is the median of the first half. The third quartile is the 75th percentile. Again, the median of the second half. We talked about this the other day. The interquartile range, Q3 minus Q1. So this is stuff we did already. I had to make sure you knew how to do this in order to do your 3-4 homework. Okay. Now, we have one last thing to talk about, and then I will be done. You know, when we made that box plot on 3-4 of the meteorites crashing down on the states, one of the things we speculated was that the very high one, 296, might have been what we call an outlier. And an outlier is just an extremely high or low data value that doesn't really fit with the rest of the data. Now, we can have what's called an observational outlier that you can sort of look at it and eyeball it and say, yeah, this one definitely doesn't fit, it's way too big. And in that data that we looked at in 3-4, maybe 296 was an outlier at the upper end, but there's actually a mathematical way to calculate the outlier, so just eyeballing it doesn't work, okay? And so in order to calculate, this is why we use the IQR, the interquartile range. What we do is we take the interquartile range and we multiply it by 1.5. And then we take that value and we're going to create boundaries with it. So we create an upper boundary and we create a lower boundary. So anything higher than the upper boundary will be an outlier. Anything lower than the lower boundary will be a low outlier. If it doesn't fall outside of those boundaries, it is not an outlier. So it might not seem to fit, but mathematically it's okay. After we multiply the IQR by 1.5, we're going to add it to Q3, the upper quartile. And that creates our upper outlier boundary. Then, in addition, I subtract it from the lower quartile. And that creates my lower boundary for my lower outlier boundary. So again, if anything is bigger than whatever I get after I add it, it's an upper outlier. If it's smaller than what I get when I subtract it from Q1, then it's a low outlier. So that's the only way to prove it mathematically. And essentially what this says is values that fall outside of those numbers, these numbers, those boundaries, are the ones that are outliers. And we're going to go through and we're going to look at the example that we did from 3-4 and see if 296 meteorites falling on a particular state is actually an outlier. So I'll work through that with you. If you want to take a picture of this data again, or if you want to copy it from your notes, that's fine. This was the exact data that we had from that problem a couple days ago. All right, the meteorites falling on the states. And like I said, one of the things we speculated after we drew that box plot was maybe 296 was an outlier. Maybe it really didn't fit with the rest of the data. And on an eyeball test, it kind of didn't. But we have to actually validate that and determine if it is or is not an outlier. So here's what we got to do. First thing we got to do is find the IQR. Okay, that's where we start. And how do I do that again? Q3 minus Q1, which is, in this case, what? What is 164 minus 47? 117, that is correct. Okay, 164 minus 47 is 117. So here's the next part. What you have to do is you have to multiply that by 1.5. So go ahead and do that. Grab your calculator, do 117 times 1.5. Figure that out, please. What do you get? 117 times 1.5. 125.5? I think it's bigger than that. 175.5, yeah. Remember, 1.5 is adding basically a half of 117 to it. All right, so that's 175.5. So what I have to do with that now is I have to add it to Q3, subtract it from Q1, and those will create my upper boundary for an outlier and my lower boundary for an outlier. Okay, so in this case, Q1 minus 175.5 is a negative. Obviously, none of my values are negative. So it would have to be more negative than this in order to be an outlier, which I don't know how that would be. I don't know how you'd have negative meteorites on your, what is that? What would that be if a negative meteorite's falling on your
Just
state?
pick it up and throw it back.
You're like throwing it back. You're throwing meteorites back into space. Okay. So we know there's not lower outliers. That's good. Now if I add 175.5 to Q3, I get 339.5. So my question is 296 an outlier? No. It's not. It falls within that range. It's not higher than this. In order for this to be an outlier, it would have to be higher than this. Well, maybe it doesn't quite fit the data, but mathematically it's not an outlier. So there's no lower outlier. There's no upper outlier. There are no outliers. Okay, so there's the work you need to show in order to prove that something is or is not an outlier.